Okay, welcome to this session about dependency management, and that's the exact time the screensaver starts. So perfect timing, right? So dependency management, model it. And like Enno said, if you're on the way to dependency hell, I'm hoping that I'm going to give you a few recipes to try to change course. So what are we talking about today? I'm going to start by a few questions. Who uses third-party dependencies? I'm expecting effectively everyone to raise their hand. That's good. So, right topic at least. How many though? More than 100? Okay. 50 something? Only a couple dozen? Just 2 or 3? Like any low-level library provider? Yep, okay. That works as well. Who has ever found getting either the right dependency or the right version in the final application, in the final setting? Okay, cool. Again, let's see about giving you some ideas about handling some of these difficulties and the way we do that within Gradle. The following at runtime. Does that ring a bell? Yep, okay. Couple person, yeah, the classical too many SLF4j implementation. I think log4j2 has a similar warning if you have too many log4j implementations. So then a bit for me in order to see how quickly I go through the first few slides. Who uses Gradle as a build tool? Oh, cool. Okay. Maven? Yeah, we're about 50-50. And both? Okay. Cool. So what I want to talk today is effectively explain to you how on the Gradle team we think about dependency management as a domain that needs modeling and needs proper handling. And so we're going to quickly go through some of the declaring dependencies. Those that are unfamiliar, or if I go too fast during that section, please raise hand, ask a question that I'll make sure to repeat and so that you can follow along. Then we'll talk about version conflict. Which is something that's already a struggle in a number of cases. And then something that we find even more interesting, which is implementation conflict, which is something that's the reality of the Java ecosystem or the JVM ecosystem at large, I would say. And we'll see what kind of solutions Gradle provides for that. So, but quickly, why am I here talking about that? So my name is Louis. I joined Gradle in 2018, and what I started when I joined the team was work for 3 years on dependency management. So a number of the features you see here, I participated from far or close, depending on the feature, and we got that released actually with Gradle 6, so which is already a couple years old, but then we realized that its usage did not pick up that much, or at least not as much as we expected. Of course, something happened in 2020 when we were supposed to go around conferences talking about that. I don't know if you remember, like that's break in life effectively for a couple of years for pretty much everyone, COVID, I think. So yeah, so that's why I'm here today trying to show you some of the things you can do. What is Gradle? Well, since 2008, the whole point is to improve developer productivity. We've got the Gradle build tool, which I work on. But we also have an enterprise product. I'm going to go quickly through those. The main thing we do are build scans. We also have that practice called Developer Productivity Engineering. If you want to know more, we happen to have a booth here, so show up at the booth and we'll be happy to have a deeper chat on that. And so that's build scans, but I've got an example that we will use during the presentation. If you want to do some challenges, you can flash that QR code. I'll show it again at the end. So, declaring dependencies. Sounds pretty easy, right? In Gradle, if you're unfamiliar with it, we actually ask you to make a number of choices from the get-go. If you look at the top, these are your production dependencies. One of them is in the API configuration, another one is in the implementation configuration. The reason we ask you to make that kind of choice is because it means something different whether we're compiling or running your code, and whether you're actually creating a library that's going to be used by someone else. Because any API dependency will want to show up in the compiled class path of your users, while the implementation stuff is effectively something that you're declaring as, this is my own business, you should not rely on that. Things that we've started doing recently with the test suite feature is actually go back to just API and implementation, but in a specific context. So here, you're adding an implementation dependency for your testing. the legacy way or the historical way of doing that in Gradle is to actually figure out the full name of the configuration, which in this case is test implementation. But what we're trying to do is, again, given a context, let's model what you're talking about, API versus implementation. So the reason for that separation is exactly what I said. We want to influence the resolution for the tasks, but also what's exposed to consumers. And I mentioned API implementation, but as you can see here, we've got a lot more, like compile only, things that you only need at compile time. Think about these nullable annotations. These are things that you just need at compile time. They don't have to be on the runtime class path when running tests, and they do not matter for consumers of the dependency. Runtime only is similar, but on the other end, it's something that you just want at runtime only, like a logger implementation, for example. And so that's why we effectively have that graph of configurations in Gradle, which is something that we see people struggle a little bit when they start in order to figure out where to put my dependency declarations. And what you see here is the green boxes are where you're supposed to declare your dependencies. The blue boxes is what is used when running things inside a project, like the compile class path for compilation, the runtime class path for running tests and things like that. And the pink boxes are the ones that will be exposed to consumers of your project. It can be something that you publish to a repository and is consumed by a completely different project, or it can just be a utilities project inside your larger project that is consumed by the other projects of your application. And you can see that what you get, either resolved locally or exposed to consumer, differs based on what was declared. So we have we're building different representation of your dependency. And again, the reason is not to annoy you with different names and many ways of doing things. It's because there is actually a reason why something that's compile-only API, for example, should only show in the API elements and the compile class path, but compile-only should just show in the compile class path and nowhere else. Was that clear? Makes sense, right? Okay, cool. So one of the things that we've introduced on the Gradle side is dependency constraints. The idea is that you're expressing an opinion about a dependency, except that you're not saying that you need it. This opinion is only valid if the dependency makes it into your graph. And so that means you're actually saying something usually about transitives. And here, what I used as an example also illustrates the fact that within Gradle, you can have rich version declaration, which express much more information than a single number. So we can see that we've got a strictly. We'll go into detail about strictly means because it has very specific use cases. But so, for example, we're using a range, then we're saying that we prefer 420 in that range. That's what we tested with locally. So if nobody else has an opinion when using that dependency, let's use that one. But for example, we also reject 421. Maybe that minor version introduced a regression that you want to, that breaks your use case. You can see also the reject all. So that's actually something that you can use on a constraint, for example, to make sure that a given dependency, which is forbidden in your setup for whatever reason, it could be compliance, like security, any kind of mandatory things that the organization you work for decides, and you could say all the versions are rejected, which means that if it ever shows up in a dependency graph, you'll get a build failure, and you'll need to figure it out, fix it, remove it, using excludes or other kind of features. But that effectively protects you from getting things that you do not want or absolutely do not want. And then the last one is quite useful when you look at reporting, because you can actually justify the reason for a dependency or a constraint, explaining why it's there, why you use a rich version, why do you have specific needs about that dependency. So some of the use cases for constraints. Central version declaration, we'll see an example where we use what we call a platform to do that. There is some overlap with a feature that we released recently, version catalogs. So when I'll share the slides, you'll have a link to the documentation. We explain why we believe having both still makes sense and when you should pick one over the other. Let's say that if you are Actually, I'll go to the alignment use case. But let's say if you're building an application, maybe the version catalog is just what you need, because nobody will consume your code. They will just see your application. And like I said, the whole idea of constraints is to influence the version of transitives. So you express an opinion without pulling the dependency in the graph. And so that means if the transitive dependency you were expressing an opinion about is no longer used by that third-party dependency's own transitive graph, it goes away, no problem, and the constraint just doesn't get activated. So, moving on to platforms. The idea here is this is not a binary that has to be executed. It's not something that provides code. It's actually a software component that only provides dependency information. And we model it as such. In the Maven world, that's what you call a BOM, which with its dependency management entries in the XML format. And here we've got something that's similar with a few differences. So first of all, the constraints can have a scope themselves. You can have API or runtime constraints, meaning that you could say, my platform gives the dependency version for all of my dependencies, but some of them should never appear outside of runtime. So I will limit the versioning to the runtime scope, meaning that if it someday pops up into one of the compile class path, it will most likely fail to resolve because you're missing the version information that you put inside the platform. Another thing that you can do with platforms is actually combine them. So here in this case, what we're doing is we're declaring an explicit dependency inside the platform on the Spring Boot dependencies BOM. And that effectively imports all of the constraints from the Spring Boot BOM into your own platform, meaning that you do not have to care about the versions for everything that the Spring ecosystem knows is working well with whatever version you were using, like I picked 278 right now, because they're there. And so the only thing you may need to add in your platform are additional dependencies that are not covered by that BOM, but have a place in your own application. Now, one of the tricky things about having that much flexibility and having that much meaning when you declare dependencies is that just like code, they tend to rot. You refactor some code, you stop using that Guava collection, but you still have that Guava dependency. You change an API in your code and you start exposing some JSON objects. Well, the JSON library you were using was an implementation dependency, but it's suddenly leaking into your API. And so it's not easy to maintain all of that. The good news is for the JVM ecosystem, there is an excellent plugin, the dependency analysis plugin, that I would strongly recommend to leverage and make it fail on violations. And it will do the kind of report that you see below. So for a given project, you will have a list of the unused dependencies that you should remove, lighter class path, whether it's compile or runtime. So faster for your IDE to index, faster for your compilation task, so effectively only benefits. Shows you transitive dependencies that you're actually using directly, which is something that all of the build tools out there allow you to do, but is also some kind of a bad practice because it means if the transitive, like the dependency that brings in that transitive stops using it, you just do an upgrade of a version and suddenly your code doesn't compile and you're chasing the why about that. Also, existing dependencies where the scope is not right. So the example I gave, you had something as an implementation, it's telling you to move it to API because it's part of your API. Or vice versa, you refactor your API the other way around. You remove this JSON object. You no longer need that JSON library to be an API dependency. It can move back to implementation. And then more even advices about things that are runtime only, where there it's also a bit saying, maybe you should remove it, maybe not, because it's hard to cover like 100% of the use cases. So now that we've discussed kind of dependency declarations, which is an important topic, let's go a bit deeper into dealing with version conflict. So what's a version conflict? Well, a version conflict happens the moment your dependency graph has multiple paths to the same dependency coordinates. The way Gradle works is it uses an optimistic upgrade strategy. So it will look at all the information it has about the version of that dependency and will pick by default the highest version that matches. That's a huge difference compared to Maven Maven has a different strategy. Their strategy is the first shortest path wins, and they do not consider anything else. And that's why you use dependency management, for example, in Maven, because then suddenly you have a one step towards a version, which is like equivalent to constraints. Again, it won't apply if the dependency isn't there, but if it's anywhere in the graph, then you suddenly have that shortest path to determine the version. And so the difference in Gradle has a few interesting consequences. And one of the things first is that some of these may sound weird. So 10, 105, we go to 105. 1020, we go to 20. So there is no real semantic versioning. Like I said, optimistic upgrade. That might not be what you want. If you've got a range and a version, then we will pick the version if it fits the range. But if you've got a range and a version that's outside of the range and lower, we will still take the latest 2.x available. So you're no longer like giving us a preferred version inside the range. So we will take the maximum when we resolve. And then you've got tools in order to make sure that resolution remains repeatable. And if you've got two ranges, you'll still get the highest of the highest range if they don't have an overlap. But if the range have an overlap, then we will pick a version that's inside the overlap. And again, this is not something that I expect you to like know by heart or everything, but it's useful information to understand why a dependency graph looks the way it is in the end after you've done your resolution. So the good thing is Gradle provides a number of tools to help you understand why a version was selected. So that's the dependency insight report. You run it with a command like the one you see below, and that's where I'm gonna use a build scan. So this would be what you would see locally. So the output of your build would show you this, and let me make it bigger. So provides a lots of information about the variant. I'm not gonna cover that today. There would be, like, it could be a single session, but as you can see, it shows you all the different versions of this org immutables value dependency that you used and all the path that led to it. And it also gives you a number of selection reasons that explain the different things. So we had a constraint at play. We also forced the dependency. We also have a constraint, which is a virtual platform. I'll refer to that later on. And we also see that we've got conflict resolutions between a number of versions. And so that allows us to understand like things like, why is there a 101 version anywhere in my graph? Well, it's here because your runtime class path uses that module duck project that you have, and they have a direct dependency on 101. If that's wrong, go fix the project, go fix or go talk to the team that produces that project. Oh, wait, I wanted to show one more thing, actually. So one of the benefits of build scans is actually that information, you always get it. So when you record a build scan, pretty much any dependency that you look into here will have that information available. So you don't have to execute a specific command. So that's one of the benefits you can have with build scans, is all of that information is available. You see the selection reasons, and you can see all the different paths. That's the more business spiel, I would say. So, a classical question, downgrading. I told you the Maven system is the shortest path, so the easiest way to downgrade a dependency in Maven is to either declare a direct dependency on it or declare an entry in your dependency management section. That will effectively use that version, nothing else. One of the downside of that, though, is that if you use the dependency management trick, it works for you. But when somebody consumes your metadata, your library published, that information is lost. It does not apply. And so the consumer would have to repeat that choice. So the way we decided to model that in Gradle is using that strictly keyword, which effectively behaves like it overruled the lower version in the graph. So it kind of works similarly to the Maven conflict resolution system. The strictly wins over anything that's lower in the dependency graph. But there is a big difference. It's actually published and visible for consumers. And I'm going to explain with graphs how that works. But so the way you do that is you can either do the explicit version strictly that you can see here, or we actually have a shortcut notation, which is the double bang, indicating that this is an enforced version, effectively. So what do I mean by downgrading and this whole graph thing? So here, again, a fake dependency graph simplified to be understandable, but you've got two dependencies, both of them require Guava. Guava had a history of having breaking changes between releases in some part of their API, so it's really tough to understand which one you need exactly. You do some testing, and you figure out that actually 19 is the one that's really needed, probably because dependency 1 uses an API that 23 no longer has, while, thankfully, dependency 2 works with 19. So what you do is you add that constraint on the Guava version. Again, it can be a direct dependency declaration, or it can be a constraint. Then you publish your library. And somebody comes, builds their application, and consumes the library. The library, effectively about Guava, says, I only accept 19. Like the library developer decided 19 is the only version that works for us. But the app also uses another dependency, which has, again, a dependency on Guava with a different version. What happens here is you get a build failure. You get a build failure because Gradle says the library subgraph says 19 is mandatory, but another subgraph of the dependency graph wants a different version. You'll have to make a choice. And so the choice, how do you make it? Similarly, the application developer will need to figure out which version of Guava works for their use case. Maybe they're no longer constrained to 19 because maybe their usage of the library does not trigger the code path that requires 19. And so once they've made that through testing, they can again express the version of Guava that they require through a strictly, and that strictly, since it starts at the app level, will effectively kind of shadows all the other declarations. Does that make sense? And so one of the benefits here is really modeling the choice you made both as a library developer and as an application developer in terms of what are my dependency needs. So another classical issue, I would say, in the JVM ecosystem is this cross-module version conflict. What do all of these have in common? I'm asking a question for real. So the whole set of Jackson libraries, like the Spring Core libraries, effectively, or the Spring Boot libraries. Sometimes they depend on each other, but mostly they're supposed to work together with a single version. You'd rather have all of the Spring Core libraries using the exact same Spring version and not have one that are like, I mean, even around minors, patch is a different case. Minors, maybe, but majors would definitely not work. And so this is what you can model as a dependency group. It's a set of dependencies sharing a version. They're designed to work that way. They've been tested that way. Like, I'm pretty sure none of these projects have cross-version testing of their own dependencies. They do have cross-version testing probably with some of their other like third-party dependencies, but not inside what they produce. And so what you really want is alignment of those versions. And the thing is, aligning dependencies requires a number of things. A group of dependencies to align, okay, so whatever you're building is in that case. Then you need a platform listing them. That's why you see projects like Jackson and the Spring projects producing bombs, because these will provide you with a guidance on all the versions that are working together. The one thing that's sometimes breaking, though, is that upgrading one may not trigger upgrading all of them. So, and the way you solve that is through a platform and a reference to the platform. So what normally happens is you only have the dotted lines, because that's what the metadata format of the pom.xml allows you to do. You can't really reference a BOM from a library and make it visible to consumers. And so what we added in Gradle is effectively that support for the fact that if a dependency references the platform, then you can imagine you've got dependency 1 gets upgraded to a version, it pulls in an upgraded version of the platform, and that automatically upgrades all of the other dependencies that you're actually using. And so you have a guaranteed alignment, effectively. So let's quickly see what that means. So I've got effectively the result of Gradle init for the application generation using multiple projects. The only modification I've made so far is I've added publishing, because that's what we want to look at, is publish metadata to understand that circular link between the platform and its components. But otherwise, we'll ignore the app module. We just have a list and a utilities module that are, basic code to illustrate the problem, but effectively, this is a leaf dependency, while utilities has a reference to the list. And so what I want to create is my platform project. I did not delete it, okay. Okay, so it's already created. So I'm gonna add the platform to my list of projects, and I can reload my Gradle build. And when I open it, when I open it, I copy the publishing block because, again, I want to publish the platform. And the first thing I do, which is the role of my platform, is my platform says that list and utilities should have the same version. Since I'm inside a given project, these are project references. The version is implied by the way it's set in the whole project. And so if I am now to publish this, and so the trick I did for publication is I've got a local repository, which is in the build folder of my root project. And so I can see here that I do have my platform. I can look at the POM file. And we see that we've got only dependency management entry for list, because there was no dependencies for list. But for example, and utilities. Yes, it's the platform. Sorry, I'm looking at the platform. I thought I was in list. My bad. So that's the platform. So the platform has effectively dependency management entries. That's the Maven version. But what I can look at also is the module file. And the module file, that's the Gradle metadata format. It effectively organizes information a little bit differently. I don't want to dive too deep into that, but let's say that API elements is the equivalent of the compile scope, so it's everything that is needed when consuming that platform for compilation. And you can see that it has dependency constraints on both list and utilities. So if I go to list, here again in the module file, I just don't have dependencies. Right? The only thing I have is a constraint on commons text, which is again something that we set up in the generated project to give you an example, but list doesn't have dependencies and the POM is exactly the same, just a dependency management entry. But what's missing there is the reference to the platform. I do not have a reference to the platform, so it means that if list has a given version, but somebody wants a higher version of utilities, list will not know about that. Just utilities will be upgraded, because utilities is the same. It's missing that backlink to the platform. It just has the list dependency. That's it, nothing else. So the way you change that is by actually simply going into your different components of that platform, and you add dependencies to the platform project. And I'm going to copy that one, it's going to be easier. And I do the same here. And so just that change effectively creates the loop, so that if I were to update list to a given version, then utilities to a higher version, utilities would point to the platform through that dependency declaration, which would bring an updated version of the platform. And since the platform has the reference to the list project as well, it gets bumped in parallel. And so just to show you the difference in terms of publication, the platform didn't change. It's the same. So it still lists the dependency constraints towards list and utilities. However, and here you need the Gradle module metadata. Here you see that you have the dependency on the platform with specific attributes, which is what says this is a platform and not a binary. Because on the POM side, you're still left with just the dependency management entry. And unfortunately, that does not translate into transitive information that is carried over to consumers. So that's one of the things that you actually need Gradle's dependency metadata format in order to benefit from the feature. But the idea is that you effectively get those cycles so that your alignment is guaranteed. I have resources links at the end that actually show you how you can even go further than that, because you can actually simulate platforms inside your own build if you know that a set of dependencies have to be aligned and they do not provide a BOM already. So we were talking about version conflict, but something that happens often also in the Java ecosystem is this implementation conflict. And the logging use case is a very good example of that. What does that mean? It means here that through transitive dependencies, you end up with too many things on your class path, and some of these things are actually incompatible. That's a nice one. There's another one with a SLF4J you can get, which is Stack Overflow. Because if you have a bridge that bridges back to and the corresponding usage, you may just end up infinite looping, trying to log somewhere. So I wrote a plugin that effectively took a snapshot of the logging ecosystem a while ago and looked at the different things that you have here. So everything that's in blue is effectively SLF4J related. Everything that's in red is more Log4j2. And then you've got pieces in between, right? You've got the legacy Log4j, you've got commons logging, and you've got all of these bridges like Java logging, Java util logging, and what the hell? Like, how do you make sense of that inside your application, especially when, for those that raise their hands, you've got hundreds of dependencies? Because the reality is that there are a number of red arrows. All of these red arrows indicate dependencies that should not be present on the class path together. They will create problems at runtime. And the problem is that figuring out problems at runtime is annoying. And so what we introduced in Gradle is the concept of capabilities. And the idea is that a given software component, aside from its coordinates and what it's known for, can provide a set of capabilities. However, there is a limitation in the dependency resolution algorithm of Gradle, which is to say a single module is authorized to provide a given capability. If more than one module provide the same capability, again, build failure, you have to figure it out. You have to see what you want to use. Something that we're thinking about for the future, which I think would be great, is to actually use capabilities as a way of expressing, I wrote a library. I did log some statements. They're useful. So when you use my library in your application, I would like, at the end, to have a logger implementation. And so you're effectively, as a library author, again, giving information to the application writer, telling him, hey, my library says interesting stuff in logs, please make sure we have a logger implementation. And of course, when you're developing the library, you do have a logger implementation in your test setup. So that condition would be satisfied for the library developer, and for the application developer, he will also see that if it doesn't provide that, the library is missing one of its requirements. That's not a reality yet, maybe one day. So how do you express capabilities? Well, they're effectively similar to dependency coordinates. A group identifier, a module name, or artifact ID in Maven Lingo, and a version. Each and every module implicitly gets its own coordinates as a capability. And what you can do is you can say, hey, I'm explicitly adding capability, so please do not take into account the implicit one, or I want the implicit capability and an extra one. Then, of course, the next step is, what do you do, right? We just broke your build. We added capabilities, and suddenly you can't compile anymore or you can't run tests anymore because dependency management fails even before that step happens. Well, there are multiple ways to resolve capability conflicts. You can say, I'm going to select the highest version because there is a versioning scheme of all the implementation of the capability that makes sense. So let's use that. Or you can actually be, I need a specific implementation. So in our case, for the logging use case, we decided to go with log4j2. So of all the conflicts possible around log4j dependencies, I'm always going to choose the log4j2 version. Let's see what that means. So, no, wrong one. So here I'm doing it again with a very simple generated Gradle project that's just a library. And the way we're gonna see what I mean is by first adding an implementation on SLF4J. Oops, what did I do? Okay, so now that I have that here, I can refresh my Gradle project so the dependency show, and I can come here. Take my logger. And of course, we want to use it, right? That's a very useful logging message, but that's illustrating the purpose, right? And so if I run that right now, like if I run the library test, the only thing I see for the moment is, oh, no SLF4J providers. Okay, so what we're gonna do is we're gonna say, oh, but then for testing, I'm actually interested in having log4j simple in play. I'm missing letters. And so that would work. But let's say that for some reason, transitively, there is someone that actually is bringing logback. Was that the one I'm supposed to use? No. Okay, so now if I run my test again, I go from no implementation to multiple providers. And that's exactly what I want to prevent. So again, like I said, I wrote a plugin that does exactly that. Capabilities. Come on. And so what I'm doing is I'm applying that plugin, and just by applying the plugin, I broke my build. Isn't that an amazing feature? So instead of having a complaint at runtime for my test, I actually broke my build. But the thing is, my build tells me exactly what the problem is. Okay, I can't resolve all the files for the configuration test runtime class path, because logback classic, which is required by the lib project, has been rejected. There is a module conflict on the capability SLF4J implementation provided by my plugin, so I decided to invent a capability that is shared by these two modules, and it says that it's also provided by SLF4J simple. And similarly, SLF4J simple cannot be resolved because, I mean, it's the other side of the conflict. you need to do something about that as well. If you had many of those conflicts, like they would all show up, because we will show you the sum of all the conflicts in the project. So the way you handle that is, and this can be scoped per configurations. So here, I'm just going to resolve it for the test runtime class path. And what I do is I access the resolution strategy. And here, I can do capabilities resolution with my capability. So we'll go back to the run result. And that's the coordinates of the capability. And what I do is select, and I say that I want to use a select4j simple. And so now, not only my build passes, but my test run and logs without a warning, because the result of the conflict has been handled. We've decided that whomever is bringing logback classic is wrong. It will no longer be in the graph. We're just going to use a select4j simple. So what I showed you is applicable to something like logging, but it's actually applicable to other real-world use cases. Who has had to deal with the Java EE to Jakarta EE migration? Okay, so a few folks still there, yeah? So they did a weird thing about dependency management. They effectively released Jakarta EE with new Maven coordinates, but fully compatible with Java EE 8. And then when they did Jakarta EE 9, they kept the same Maven coordinates as the Jakarta EE 8 release, except that nothing is compatible anymore. It's like different packages. So these two things means that it's certainly something that you have to handle depending on your graph of dependencies, because if some of your dependencies uses Jakarta E8, others uses Java E8, you end up with duplicate classes on the class path because they belong into jars that have different coordinates. That's a perfect use case for capabilities again. And so there is a plugin created by folks in the community that you can add to your project, and it will flag all of these conflicts, potentially breaking your build and then asking you, what do you want to do? And then you use the API I just showed you to decide how to resolve the conflict. My recommendation today, given the situation, would be stick with Java EE8 if you're, again, still on the Java X packages. Then between EE8 and 9, here the problem is that with the optimistic version upgrade, you would get totally incompatible jars, because something that was using Java X suddenly used Jakarta as the start of the package, meaning your code doesn't run anymore. Here again, you can use Gradle techniques. So one of them is the substitution feature of Gradle that I did not cover in detail, but it effectively allows you to say, if you see that package, replace it with another one. And it can be version specific. So I would recommend to always replace the Jakarta E with Java E things for Java E8. And also, what I showed you about the reject all, you could make sure that your build in its platform rejects all the Jakarta E8 artifacts. Like their specific version should never enter the graph because it's bringing trouble. There are more use cases for capabilities. The whole multiple implementation case, so ASM, for example, they changed their coordinates. That's one way you can add a capability to make sure that you never get both. You've got the CGLib versus CGLib nodep. Having both on the class path is a problem. And you've got many more. And the plugin I explained about the Jakarta Java E mess actually covers quite a large number of ecosystem-specific rules that are potentially applicable to all of your builds. And so just applying that plugin may report issues that then you can act upon by using the resolution API. Another thing that we do with capabilities that I won't have time to cover today is the modeling of optional dependencies, or what we call feature variant. Again, when I'll share the slides, we've got a link to the documentation. Please take a look. That's also something which is really interesting. And that's effectively what I wanted to give you today. There is a whole lot more in Gradle around dependency management, but we only have 50 minutes, and I wanted to have a few minutes for questions at least. I'll leave you up with these resources. Also, when I share the slides later today, you will be able to look at them. But yeah, so I do have a few minutes for questions then.
Why does it look like the dependency is a free text string?
Why does it look like the dependency is a free text string? Because I decided to not add one more concept, which is version catalog, introduced recently. But you can use free version string if you want, but I would effectively recommend today to actually use version catalogs where you would use a text file which just lists the dependencies that you can use in your project, and then you actually have an API to autocomplete their names. So that's kind of the historical, but I didn't want it to add yet another concept in the sake of time. But yeah, go check out version catalogs. Yes?
So you didn't have time to go into that dependency Jakarta JavaX issue,
yeah.
And you have links to that?
Yes, I've got links in the resources to both an article and the plugin itself explaining what it does and why it does it.
Yeah, but basically it can help you replace, you can infill like Jakarta dependencies to JavaX.
Yeah,
as a use case.
Yes, exactly.
Yeah.
It effectively helps you detecting that you have the problem. Then the solution is actually depending on the application you're writing.
Yeah.
Like there is not necessarily a solution.
Thanks.
Thank you. Thank you.